Hello everyone, this talk is about weighted automata over fields, and in particular about the power of restricted ambiguity in such automata. Let us start by briefly recalling an informal definition of weighted finite automata. This can be described as ordinary non-deterministic finite automata, in which in addition some quantities, or so-called weights, are assigned to each arrow of the transition diagram. This means that a weighted automaton can look like this. We see that there indeed is a weight assigned to each transition, and, in addition, there is an initial weight assigned to each initial state. Similarly, there is a final weight assigned to each final state of the automaton. These weights don't have to be numbers, but they can be taken from some more general algebra, which is usually assumed to be a semiring, in which case the behavior of the automaton, or in other words its semantics, is defined in a reasonable way. In particular, the value of a single run of an automaton is obtained by multiplying the weights of arrows composing the run, including these short arrows designating initial and final states. The actual value assigned by an automaton to a word W over the underlying alphabet is then obtained by summing up the values of all runs of the automaton in which the word W is read. We don't allow transitions on the empty word, so the sum is always finite. This means that a weighted automaton no longer just recognizes a language, but the object that it realizes, that is the behavior of A, is a function assigning elements of some semiring S to words over the underlying alphabet sigma. When the Boolean semiring is taken from S, we essentially obtain the usual non-deterministic finite automata, and the behavior of any such automaton essentially represents a language. More precisely, it is a characteristic function of a language. And for this reason, we usually aim to equip the functions from sigma star to S by an algebra generalizing the usual algebra on languages, which is something that the standard algebra on functions doesn't fulfill. And this leads to an idea of viewing the behavior of a weighted automaton as a non-commutative formal power series. We don't have to go into details here, but let us note that this viewpoint has some notational consequences. In particular, we denote the value of the behavior of A on a word W like this, and we call this value the coefficient of W in the series realized by A. A series is called rational if it is realized by a weighted finite automaton. Now, every weighted automaton with state set consisting of numbers from 1 to some n can also be unambiguously described by a so-called linear representation, which consists of a row vector of initial weights, a column vector of final weights, and, for each letter C, of a matrix containing weights of transitions upon C between particular states of the automaton, while missing arrows are understood to be of weight 0. And there is a well-known characterization of the behavior of A in terms of its associated linear representation, which says that the coefficient of a word in the series realized by an automaton A is given like this. That is, we first take the row vector of initial weights, then we multiply it by matrices corresponding to particular letters of the word, and finally we multiply the resulting row vector by the column vector of final weights and obtain the desired coefficient. In case the alphabet under consideration is unary, this characterization admits a simple form involving the vectors I and F and the power of the single matrix needed to describe the transitions of the automaton. An alternative way to formulate this observation is to say that unary weighted automata can also be seen as systems of linear recurrences, given like this. In fact, unary weighted automata are strongly related to linear recurrence sequences, and this observation can be used to derive most of these connections. The key notion for our later considerations is that of an ambiguity degree of a weighted automaton, which is defined in exactly the same way as for ordinary non-deterministic finite automata without weights, and which is given by a function counting the number of successful runs of an automaton on a given word, where the run is said to be successful if it leads from an initial state to a final state. It is easy to see that this definition actually doesn't depend on weights at all, which means that some known characterizations of classes of automata with restricted ambiguity can be applied to weighted automata as well. The classes of k-ambiguous, unambiguous, finitely ambiguous, and polynomially ambiguous weighted automata are defined in the same way as for finite automata without weights. However, there is a significant difference between the weighted and the unweighted setting. While all these restrictions are equally powerful for finite automata without weights, this might no longer be the case for weighted automata, where restrictions on ambiguity might actually decrease the expressive power of the model. In fact, the study of expressive power of weighted automata with restricted ambiguity is the main topic of this talk. In addition to their purely theoretical relevance, the motivation for studying weighted automata with restricted ambiguity comes, for instance, from the study of some decision problems, either for automata or for linear recurrent sequences, which are related to unary weighted automata. Moreover, some classes of weighted automata with restricted ambiguity arise also in the study of weighted first-order logics of Drost and Gaston. If we adopt this notation for classes of series realized by weighted automata with restricted ambiguity, then the following two hierarchies become natural objects of study. First of all, the so-called ambiguity hierarchy is composed by the unambiguous, the finitely ambiguous, the polynomially ambiguous, and the unrestricted rational series. Secondly, there is a hierarchy of k-ambiguous series for all positive natural k, which we may call the finite ambiguity hierarchy. While all these inclusions are self-evident, it is natural to ask which of them are strict for given S and sigma. The answer may depend both on the semiring S and the alphabet sigma, and there has already been some research on this problem for certain particular semirings. It is known that the ambiguity hierarchy is strict over the semiring of natural numbers, the field of rational numbers, and the min plus and max plus semirings of naturals. The finite ambiguity hierarchy is known to be strict over the rationals as well, but on the other hand, it is clear that both hierarchies collapse over locally finite semirings, as it is well known that all weighted automata over such semirings can be determinized, while all deterministic automata are unambiguous. For our purposes, the most important of these particular cases is that of automata over the rationals. The ambiguity hierarchies over the field of rational numbers have been systematically explored by Barlow and others, who have established their strictness already over unary alphabets. In fact, these authors have approached the problem from the viewpoint of linear recurrent sequences, and similar results have also been independently obtained by Drost and Gastin and by Mazowiecki and Riveros. To separate the set hierarchies, Barlow and others have shown that the rational generating function of the Fibonacci numbers is not polynomially ambiguous. They claimed that the generating function of this simple arithmetic sequence separates the polynomially and finitely ambiguous series. And finally, they claimed that the generating functions of sequences like this separate the levels of the finite ambiguity hierarchy. The main purpose of this talk is to open a question that has not been raised so far. Namely, we ask what are the relations between particular levels of ambiguity hierarchies over a general field. This is a natural question, as automata or fields are one of the best understood classes of weighted automata. Moreover, it would be interesting to know under which conditions the arguments of Barlow and others for automata over the rationals do generalize. The answer to our more general question obviously depends on the field. For instance, both hierarchies collapse over locally finite fields, while we have seen that they are strict over the rationals. Moreover, the answer can also depend on an alphabet. In this talk, I am going to present one part of a broader research trying to answer the proposed question. The other part is not published yet, and it deals with the relations between polynomially ambiguous and unrestricted unary weighted automata. It can be proved that both are equally powerful over algebraically closed fields, while over other than algebraically closed fields of characteristic 0, polynomially ambiguous automata are strictly less powerful. On the other hand, we are now going to deal with kind of complementary questions. Namely, we aim to shed some light on the relation between finitely and polynomially ambiguous weighted automata over fields, explore the conditions under which the finite ambiguity hierarchy over fields is strict, and also relate finite ambiguity in weighted automata over fields, or more generally over commutative semirings, to finite sequentiality. At this point, let us recall that an automaton is said to be k-sequential for some k if it is an otherwise deterministic automaton with at most k initial states. The automaton is said to be finitely sequential if it is k-sequential for some k. We mostly consider the case of unary alphabets, but our findings will also have some implications for the case of general alphabets. We will rely on the known characterizations of polynomially and finitely ambiguous finite automata, which also apply to weighted automata, and in particular on their specializations for unary alphabets. First, recall that an automaton is polynomially ambiguous if and only if it doesn't contain a state q with two distinct runs from q to q upon the same word w. For unary automata, this is equivalent to the conditions of all strongly connected components of the automaton being either directed cycles or single vertices without a loop. Next, An automaton is finitely ambiguous if and only if it doesn't contain distinct states P and Q, such that there are runs upon the same word from P to P, from P to Q, and from Q to Q. For unary automata, this means that in addition to the condition of all strongly connected components being directed cycles or single vertices, there is no run of the automaton passing through two different directed cycles. Given these observations, we might define a natural structural measure of a unary finitely or polynomially ambiguous automaton, which is given by the number of directed cycles that it contains. We call such an automaton a k-cycle automaton if it contains at most k directed cycles. We may now observe that every trim finitely ambiguous k-cycle automaton can be decomposed into k one-cycle automata in the sense that the set of successful runs of the original automaton is a disjoint union of the sets of runs of the automata forming the decomposition. This implies that the behavior of the original automaton A is the sum of the behaviors of the corresponding one-cycle automata, and the same holds for its ambiguity degree. The proof of this observation is based on a simple construction in which the automaton Aj is obtained by modifying the automaton A so that only the runs visiting the cycle number j, whatever it is, can be successful. We are now only possibly left with runs not visiting any cycle, which may be adjoint, for instance, to the automaton A1. Let's now take a look at the relation between finitely ambiguous and finitely sequential unary weighted automata, which can be uncovered already in the relatively general setting of commutative semirings. First, let us prove that a finitely sequential one-cycle unary automaton, A over a commutative semiring, is always necessarily determinizable. This is trivial if A contains no cycle, but if A contains a cycle, then there is a threshold t0 such that for all t greater than t0, any successful run of A upon c to the power of t goes around the cycle at least this number of times. Every such run first follows some run gamma 1 from an initial state to q, then goes around the cycle the set number of times, and finally follows some other run gamma 2 from q to a final state. The point is that the total length of gamma 1 and gamma 2 depends only upon the remainder after dividing the length of the run minus t0, that is this value, by the length of the cycle, and that the finite set of all possible pairs of gamma 1 and gamma 2 depends only on this remainder as well. By commutativity of the semiring, the weights contributed by these runs gamma 1 and gamma 2 can be accumulated into some constant bs, depending on s, that is the remainder after the division, and the coefficient of the word c to the power of t can be expressed like this, where M is the product of weights of transitions forming the cycle. Thus, if we denote like this the coefficients of the first few words in the series realized by the original automaton, we may realize the same series by the following deterministic automaton, which proves the lemma. As a consequence, we find out that every finitely ambiguous unary k-cycle automaton over a commutative semiring is equivalent to some k-sequential automaton. For a proof, it suffices to decompose the k-cycle automaton into one-cycle automata and take the disjoint union of their equivalent deterministic automata. We can also conclude that every finitely ambiguous unary weighted automaton over a commutative semiring admits a finitely sequential equivalent, which is certainly not true over larger alphabets. Let's now finally consider unary weighted automata over fields. As we have already noted, the coefficients of words in series realized by such automata can be expressed using the power of a single matrix corresponding to the automaton. Alternatively, this can be expressed by saying that the coefficient sequence of the automaton's behavior can be determined from the solution of an initial value problem for a system of linear difference equations. It then follows by standard linear algebra or by the standard theory of linear difference equations that the coefficients of words in the behavior of A can be expressed in the following form, that is, as a linear combination of polynomial exponential functions. Here, sigma denotes the spectrum of the matrix A over the algebraic closure of F. Alpha of lambda denotes lambda's algebraic multiplicity as an eigenvalue of A. And the A's are constants from the algebraic closure of F that are uniquely determined by the first n values of the resulting sequence, which we may call initial conditions. Most of these observations follow by equivalence of A to a matrix in Jordan canonical form and by the form of powers of such matrices. Moreover, distinct polynomial exponential functions occurring in these representations are always linearly independent. Let's now take a look at the finite ambiguity hierarchy over general fields. Barloy and others claim strictness of this hierarchy over the rationals, and we now show that their example can be modified to work over an arbitrary field that is not locally finite. This implies that we have to use a proof technique that is largely independent of the field under consideration, which is probably the main technical complication in what follows. First, note that a field that is not locally finite always contains an element of infinite multiplicative order, that is, an element whose non-negative integer powers are pairwise distinct. It is known that such an element exists already in every other than locally finite commutative semiring, and for fields, its existence follows also by an observation that a field that is not locally finite either contains the isomorphic copy of the rationals or an element that is transcendental over its prime subfield. Now we claim the following. Let f be a field that is not locally finite, k a natural number, and alpha an element of infinite multiplicative order. Then the series defined like this is k plus 1 sequential, but not k ambiguous. Let's now prove this proposition. The proof of k plus 1 sequentiality is easy, as it is immediate that the series can be realized by the following k plus 1 sequential automaton. Now, the trickier part is to prove that the series is not k ambiguous. For a contradiction, suppose that it is realized by some k ambiguous automaton A. Strongly connected components of this automaton are either directed cycles or single vertices without a loop, and consider the matrix of its linear representation. It then follows by linear independence of the pairwise distinct polynomial exponential functions that this matrix has to have the first k plus 1 powers of alpha as eigenvalues. Moreover, by the form of the characteristic polynomials of directed cycles, every cycle of the automaton can give at most one of these eigenvalues. Hence, the automaton has to contain at least k plus 1 different cycles. Let's decompose the automaton into one cycle automata, and then, after some technical analysis, we find out that those of these one cycle automata which have an eigenvalue of the form alpha to the power of d times a root of unity must give alpha to the power of dt for all sufficiently large t when their behaviors are summed up. These values are always non-zero, so there must be a successful run of any sufficiently large length in some of these automata, and as this holds for all d, and the runs of A are distributed between the automata of the decomposition, there have to be at least k plus 1 successful runs of A on sufficiently large words, which contradicts k ambiguity of the automaton A. Given the property that we have just proved, we may directly conclude that the finite ambiguity hierarchy of a field f is strict whenever f is not locally finite, and that the same holds for the finite sequentiality hierarchy as well. Moreover, both hierarchies trivially collapse over locally finite fields, so the conditions for strictness of the finite ambiguity hierarchy have been completely characterized by our observation. Now let's take a look at the relation between finitely and polynomially ambiguous weighted automata over fields. Let's first observe that the example provided by Barlow and others for automata over the rationals actually works for all fields of characteristic 0. That is, consider a series such that the coefficient of c to the power of t is t. We show that this series is polynomially ambiguous, but not finitely ambiguous over fields of characteristic 0. Polynomial ambiguity is very easy to establish, as the series is obviously realized by the following polynomially ambiguous automaton. Now let's suppose, for contradiction, that the series is realized by a finitely ambiguous automaton A. Once again, decompose this automaton into one-cycle automata and observe that the non-zero eigenvalues of this automata are all roots of polynomials like this, which are separable over fields of characteristic 0. This means that each of the automata of the decompositions has simple non-zero eigenvalues. As a result, the uniquely determined expression for the coefficients cannot contain a linear term, and hence the automaton cannot realize the series R. Finally, let's briefly touch upon the same problem over fields of positive characteristic, which seems to be far more interesting. We just make a first step towards this understanding by showing that the series realized by unary, polynomially ambiguous weighted automata over an algebraically closed field of positive characteristic cannot be separated from series realized by unary, finitely ambiguous automata over the same field. In other words, let F be an algebraically closed field of positive characteristic P, and A a polynomially ambiguous unary weighted automaton over F. We show that A necessarily admits a finitely ambiguous equivalent. The characteristic polynomial of A necessarily takes the displayed form. Here the factors x come from strongly connected components composed by single vertices without a loop, and the less trivial factors come from strongly connected components taking the form of directed cycles. As F is algebraically closed, all roots of these polynomials, that is, the eigenvalues of the automaton, are in F. For all k from 1 to s, let sigma k consist of those roots of the kth factor of the big product which are not contained in previous sigmas. Moreover, let sigma 0 contain 0 if it is an eigenvalue, and otherwise let this set be empty. Now the behavior of A can be written as a sum of series Rk, where each of the summands can be written as a linear combination of polynomial exponential terms involving just the eigenvalues from sigma k. It clearly suffices to show that each of the series Rk is finitely ambiguous. This is clear for k equal to 0. And for the remaining case, we show that the series Rk is in fact realized by a deterministic automaton, which is necessarily finitely ambiguous. To establish this fact, we construct an automaton Ak such that every element of sigma k is its eigenvalue, and the algebraic multiplicity of each such lambda is at least alpha lambda. That is the original algebraic multiplicity of this eigenvalue. In other words, the automaton AK will have enough eigenvalues to get this expression for Rk as its behavior. If we then make sure that the initial coefficients in the behavior of AK coincide with those in Rk, we get the equality of both series by uniqueness of the coefficients. It thus suffices to construct an automaton with the above listed properties. Let lowercase m satisfy this inequality for all lambdas in sigma k, and define uppercase m and b like this. Moreover, for the first m values of t, denote the corresponding coefficient in Rk by Vt. Now let Ak be a deterministic automaton taking the form of the following directed cycle. Then it is immediate that the behavior of Ak coincides with Rk at the first uppercase m coefficients, and moreover, the characteristic polynomial of the matrix of Ak is given like this, where the last equality follows by the fact that we are working over a field of characteristic P. As every element sigma k of sigma k is a root of the polynomial whose power is being taken, the matrix of Ak indeed has enough eigenvalues, and it follows that this automaton realizes the series Rk, so that the theorem is finally proved. Nevertheless, when it comes to the relation between polynomially and finitely ambiguous weighted automata or fields, there are still some cases left open. First, it would be interesting to know about the relation between these two classes of automata over algebraically closed fields of positive characteristic and of a larger than unary alphabet. Moreover, we have not even touched upon the relation of these two classes of automata over fields of positive characteristic that are neither locally finite, in which case the situation is trivial, nor algebraically closed. Thanks for watching.